Welcome back, calculus friends. This is section 3.6, day 1 notes. So today we're going to learn about a new kind of differentiation that we haven't done before, which is called implicit differentiation. And the idea behind it is, what if we have a function that we want to find the derivative of, but we can't make the function look like y equals and have everything in terms of x on the other side of the equal sign? For example, we have this function here, x cubed plus y cubed equals 6xy. There's no way to make this equation look like y equals. We could try all day, but algebraically we'll never be able to isolate y alone on one side of the equal sign. But it's not necessary to do that. In order to find the derivative of a function like this, we can use something called implicit differentiation, which means that we differentiate both sides of the equation with respect to x, and then we solve the resulting equation for y when we're done, okay? But one thing that we need to keep in mind whenever we're going to be doing implicit differentiation is that we are assuming that y is a function of x. Okay, so when we do our differentiation and we have a term with y, okay, so anytime we differentiate a term containing y, we have to apply the chain rule. And multiply by y prime or dy dx. The derivative of y with respect to x. And on that note, this is just a notation thing, okay? So remember, y prime is equivalent to dy dx. That is the derivative of y with respect to x. Okay, so we could use, when we're doing the chain rule part of the implicit differentiation, we can multiply by the derivative of the y term, which would be y prime, or dy dx. And I will use both notations in the notes just so that you get comfortable with both of those things, okay? So just keep this in mind, that y prime and dy dx mean the same thing. So I think that the easiest way to explain implicit differentiation is to just show you an example of what we mean, okay? So in the first example, at part A, it says find y prime by implicit differentiation, which again means that we are just going to take the derivative of both sides of the equal sign with respect to x. So the first step in implicit differentiation is showing what you are doing. So I'm going to say that I am going to do dy dx of the left-hand side, which is xy plus 2x plus 3x squared. And that's going to be equal to the derivative dy dx of the right-hand side. And so now I differentiate each term. Now keep in mind, every term that I differentiate may have its own differentiation rules associated with it. So basically on the left-hand side, because I have three terms being added together, I am going to take the derivative of the first term with respect to x. I am going to take the derivative of the second term with respect to x, and I am going to take the derivative of the third term with respect to x. And this isn't a step that you would probably typically show on your paper, you know, kind of putting that dy dx with each term, but I'm just sort of illustrating to you what I'm doing as I'm doing it. And so now when we think in terms of differentiation, our first term here has an x times a y, so when we differentiate that, that's going to require us to use the product rule. Our second term is just 2x, so that is going to use the power rule. Our third term, 3x squared, is also going to use the power rule. And then our fourth term here, dy dx of 4, that's just the derivative of a constant. All right, so now let's actually do this differentiation. So the derivative of x times y, product rule, first d second plus second d first. So I'm going to get first, which is x, d second. So again, y is a function of x. So the derivative of y is going to be, we could either write it as y prime or we could write it as dy dx. So in this case, I'm going to use the y prime notation. So x times y prime plus, and then second, which is y, times the derivative of the first, and the derivative of x would be 1. Then the next term, derivative with respect to x of 2x, is going to be 2. And the third term, the derivative of 3x squared with respect to x, is going to be 6x. On this side, the derivative of a constant term is 0. All right, so now the next step in this process would be to solve this resulting equation for y prime. So any term that does not contain y prime, I'm going to move to the other side of the equal sign. So my first term is x times y prime, but then the other three terms, y times 1 is y, and then 2, and then 6x, all of those do not contain y prime, so I am going to subtract them over to the other side of the equal sign. So x times y prime is equal to negative y minus 2 minus 6x. And the order of the terms doesn't matter as long as you have the right signs. And then if I want to solve for y prime, I have to divide both sides of the equation by x. So my derivative, my y prime, is going to be equal to, and just a little algebraic trick here to make this look a little bit nicer, since all three terms in my numerator are currently negative, what I'm going to do instead is factor out that negative 1 from all three terms, and then I'm just going to put it in the bottom with the x, which would make my three terms in my numerator now positive. And it's just a little bit more visually appealing that way. But you could certainly have left all three terms negative in your numerator and then just divided by x in your denominator. So here's our resulting answer, y prime. This is the first derivative of the given function in example 1. Okay, now you may have noticed if you looked carefully at this example that I could have isolated y for this particular function because y only appears one time in the equation in the first term. So I could have gotten y alone and then done regular differentiation. And so that's actually what they're asking us to do in part B. So I am going to solve the equation for y first, and then I'm going to differentiate to get y prime in terms of x. So if I were to solve this for y, again, the first step would be to move any terms that don't contain y over to the other side of the equal sign. So I would have xy is equal to 4 minus 2x minus 3x squared. And then I would divide everything by x. So my equation would be y equals. Now, since I know I'm going to want to differentiate this, and since I'm dividing by a monomial, I am going to rewrite my equation, my y equals, as all powers of x in my numerator so that I can apply the power rule rather than having to use the quotient rule. So my first term would be 4 divided by x, which if I bring that x upstairs is 4x to the negative 1 power. My second term, negative 2x divided by x, is just negative 2. And my third term, negative 3x squared divided by x, is just going to be negative 3x. So now I can easily find my y prime just using the power rule. So my y prime is going to be, for my first term, bring down the negative 1, multiply it times the 4. We're going to get negative 4x to the negative 2. My second term, the derivative of a constant is 0, so that negative 2 disappears for my derivative. And then my third term, the derivative of negative 3x is negative 3. And then, of course, I can write my first term as negative 4 over x squared minus 3. Okay, so you might be saying right now, well, gosh, the answer that I got for part B does not look the same as the answer that I got for part A. And that's absolutely correct because our answer from part A has a y term in it. And our answer for part B does not have a y term in it because we solved for y. So that brings us to part C. Part C wants us to, here we go. Part C says, check the solutions to part A and part B and show that they're consistent by substituting the expression for y from part B into the solution from part A. Okay, so here's what we found y was equal to, right? We found that that is what y is equal to from part B. So if I take my solution from part A, which my solution from part A was y prime is equal to y plus 2 plus 6x, all divided by negative x. If I substitute that expression for y in and then I simplify, I should end up with the same result as I got from part B. So let's find out. So this would mean that y prime is equal to 4x to the negative 1 power minus 2 minus 3x, that's my y, plus 2 plus 6x, all divided by negative x. And again, so now I think I'll combine like terms first, because I do have a few like terms in my numerator. Notice that the negative 2 and the positive 2 cancel out. And then I have a negative 3x and a positive 6x, so that's going to give me a 3x. So I have 4x to the negative 1 power plus 3x divided by negative x. Well, if I simplify that, 4x to the negative 1 divided by negative x. Well, if I move that x downstairs, that's going to make my term negative 4 over x squared. And then my second term, the 3x divided by negative x, that's just going to turn into negative 3. So as you can see, when I did that substitution for what y was equal to, now my answer looks exactly the same as the answer that I got in part B, which basically this exercise was just proof that implicit differentiation does work. It gives us an answer that looks different but is equivalent to the answer if we could isolate y. Now again, this particular example was unique in that we were able to solve our equation for y and compare the two methods. We're not always able to do that as in our next examples, but that is why implicit differentiation is an important skill to have in calculus, because we often want to differentiate equations where we can't solve for y. So let's take a look at the next example, example 2. It says find dy dx by implicit differentiation. So I'm going to start this problem exactly the same way I started the previous. I am going to show what I'm doing. I am taking dy dx of the left-hand side of this equation and dy dx of the right-hand side of this equation. And when I do so, again, I am just differentiating each term individually. So on the left-hand side, again, my first term is going to be power rule. My second term, here, this is power rule. My second term is going to be product rule. My third term is going to be power rule. But because it's my y term, it's also going to be chain rule. And once again, over here, we just have derivative of a constant. Okay, so let's do the differentiation. The derivative of x squared is going to be 2x. The derivative of xy, I have to do first d second plus second d first. So that's going to be first. Derivative of y is y prime, so first d second, plus second, that's my y, d first, derivative of x is 1. Okay, so there's my product rule. Then the derivative of negative y squared, well, first it's the power rule, so that's going to be negative 2y to the first, but then I have to multiply by the derivative of y, which is y prime, right? There's my chain rule. And then on the other side of the equal sign, the derivative of a constant term 4 is 0. Okay, so now this time, after I simplify, let's see, I have 2x plus xy prime plus y minus 2y y prime equals 0. So in this particular problem, I have two terms that contain y prime. So I want to move the other two terms, the ones that don't contain y prime. So my 2x and my y, I want to move those over to the other side of the equal sign. And then the two terms that contain the y prime are going to stay on the left-hand side, but I'm going to factor that y prime out. So on the left-hand side of xy prime minus 2yy prime, if I factor out the y prime, then I'm going to have x minus 2y. And then on the right-hand side, I'm going to have the negative 2x and the negative y. And then because I'm trying to solve for y prime, that's why I factored it out on the left-hand side. Now I'm going to divide both sides by that family, x minus 2y. So my answer to my derivative is going to be y prime is equal to negative 2x minus y divided by x minus 2y. Continuing on, example 3 is more practice of the same. So begin by showing what we are doing. We are doing dy dx of the left side, x to the fourth times x plus y, and dy dx of the right-hand side, y squared times 3x minus y. And notice that on both sides of the equal sign here, we have products, right? So this here is going to be product rule. And over here, we're going to have product rule, and we're going to have some chain rule. Okay, so we are going to do some very slow, careful algebra because we've got a lot of terms going on here. So on the left-hand side, if we are doing the product rule, first d second plus second d first. So again, my first is x to the fourth. My second is x plus y. Okay, so first d second is going to be x to the fourth. And then derivative of x plus y, well, that's going to be 1 plus, and the derivative of y is going to be y prime. This time I'm going to use dy dx notation just to mix it up. Means the same thing as y prime, right? So that's first d second plus, now I need second d first. So x plus y, and the derivative of the first, the derivative of x to the fourth, is going to be 4x cubed. Okay, so left side is done. Now let's do the right side. First d second plus second d first. So first, y squared. D second, derivative of 3x is 3. The derivative of negative y is going to be negative dy dx. Okay, so first d second plus second, so 3x minus y. D first, the derivative of y squared is going to be 2y. But again, remember that y is a function of x, so we have to multiply by the derivative of y. There's our chain rule, so times dy dx. Okay, so now we have some cleaning up to do here. We have some distributive property on both sides of the equal sign. X to the fourth times 1 is x to the fourth. X to the fourth times dy dx is x to the fourth dy dx. Plus 4x cubed times x is 4x to the fourth, and 4x cubed times y is 4x cubed y. This is equal to y squared times 3 is 3y squared, and y squared times negative dy dx is negative y squared dy dx. And then finally, 2y dy dx times 3x is going to be 6xy dy dx. And 2y dy dx times negative y is going to be negative 2y squared dy dx. All right, so in this problem, I have chosen to use the dy dx notation. And so I would like to solve for dy dx, which means that I want to put all of my terms that contain dy dx on the same side of the equal sign. And I want to put anything that does not contain dy dx on the other side of the equal sign. All right, again, you can move them to either side that you want, but obviously, you want it to be as little work as possible. So I am going to choose to collect my dy dx terms on the right side of the equal sign, since I already have 3 of them over there. So that term is going to get moved over to that side. And then the only term on the right-hand side that doesn't contain dy dx is that 3y squared, so that is going to move over to the left side. So starting on the left side, I'm going to have x to the 4th plus 4x to the 4th. I'll combine like terms in a second, plus 4x cubed y, and then if I'm moving that 3y squared over, I will subtract minus 3y squared. Equals. Now I'm moving my x to the 4th dy dx, so I'm going to write that term first, negative x to the 4th dy dx minus y squared dy dx plus 6xy dy dx minus 2y squared dy dx. Okay. I have some like terms on the left and on the right. On the left-hand side, 1x to the 4th plus 4x to the 4th makes 5x to the 4th. On the right side of the equal sign, I have a negative y squared dy dx, and I have a negative 2y squared dy dx, which is going to make negative 3y squared dy dx minus x to the 4th dy dx plus 6xy dy dx. And then my next step is going to be, let's factor that dy dx out of all of the terms on the right-hand side. So if I factor out dy dx, then I have negative 3y squared minus x to the 4th plus 6xy. And on the other side here, I obviously have my 5x to the 4th plus 4x cubed y minus 3y squared. And so then the last step is going to be dividing by the terms that I have in the bracket, the negative 3y squared minus x to the 4th plus 6xy. I'm going to divide both sides of the equal sign by that, so I'm just going to go ahead and sneak my answer up here in the corner. My dy dx is going to be equal to, in my numerator, I will have 5x to the 4th plus 4x cubed y minus 3y squared. And that is going to be divided by negative 3y squared minus x to the 4th plus 6xy. And again, the order of the terms in the numerator and the order of the terms in the denominator does not matter as long as you have the correct signs attached to each term. One more example here to practice our implicit differentiation. This one has some e's in it and some trig in it. All right, so we're going to begin the same way we always begin. We are going to show that we are taking dy dx of the left, which is e to the y times cos x, and we are taking dy dx of the right, which is 1 plus sine of x times y. All right, so on the left-hand side, we're going to be using product rule with chain rule. And on the right-hand side, we're going to be using trigonometry or trigonometric derivatives with the chain rule and the product rule. So we've got a lot going on here when we differentiate. We're going to take our time. Okay, so on the left-hand side, we have a product, first d second plus second d first. So when we do our derivative here, first is e to the y. Derivative of second, so the derivative of cosine x would be negative sine x. Plus second, so that's cos x, d first. And the derivative of e to the y is e to the y, but that's also chain rule because our exponent is y, which is a function of x. So then we need to multiply by dy dx, or y prime, whatever you prefer. On the right-hand side, derivative of 1 is 0. The derivative of sine xy, now this is going to be chain rule. So the derivative of sine is cosine. So we have cosine of x times y. But then we have to multiply by the derivative of what's inside of the cosine. And what's inside of the cosine is a product. So we're going to have to do the product rule on x times y, which is first, that's x, d second, derivative of y is dy dx, plus second, that's y, and d first, derivative of x is 1. All right, now let's clean this up. We have negative e to the y sine x plus e to the y cos x dy dx equals cosine of x times y times x dy dx plus cosine of x times y times y. And in the next step, I'm going to put the x and the y in front of those cosines just because I don't like them after. But notice that I did parenthesize the x times y inside of the cosine because I want to make sure that it's very clear that both of those are inside of that trig function. Okay, so now I'm always wanting to get my dy dx's on the same side so that I can solve for dy dx. So I'm just going to do some rearranging of terms. I'm going to have my e to the y cos x dy dx. And then I'm going to move this term right here, x cos xy dy dx, over to the other side. So I will be subtracting it. So minus x cos xy dy dx, okay? And then I have my equal sign, and so now I have to move this first term over. So if I move it over, I'm adding it. So it'll be positive e to the y sine x, and then I have plus, I'm going to put that y in front, y cos xy. All right, let's factor out our dy dx on the left-hand side, which gives us e to the y cos x minus x cos xy equals, and over here we just have e to the y sine x plus y cos xy. And then, of course, the final step is to divide both sides by what's in the bracket. So once again, my final answer here, I'll put it up at the top, is going to be dy dx is equal to, my numerator will be e to the y sine x plus y cos xy, and my denominator will be e to the y cos x minus x cos xy.